Welcome back to the deep dive. We are doing something a little different today. Usually when we talk about aviation or engineering, we're looking at the glamour shots, the high bypass turbofans or the composite wing
Gosh, the
structures.
things that look great on a brochure.
Exactly, the glass cockpits that look like spaceships. But today I want to go underneath the floorboards. I want to look at the nervous system of the aircraft.
It is the perfect analogy because without this system, those engines are just dead weight. The glass cockpit is just dark glass. The aircraft is essentially a very expensive, very heavy paperweight sitting on the tarmac.
We are diving deep into ATA Chapter 24, electrical power. But we aren't doing a general overview of generators and batteries. We are looking specifically at circuit control and protection. And I know I can hear some of the listeners right now saying, switches and circuit breakers. Really? Is this going to be dry?
Well, if you think it's dry, you really aren't looking close enough. When you actually look at the physics, the violence of what happens inside a switch when you break a high current circuit.
The microscopic threats too, right?
Exactly. Things like tin whiskers that can bring down a satellite or a jet. I mean, it is anything but dry. It's about thermodynamics, electromagnetism, and catastrophic risk mitigation.
It's about keeping the fire inside the wire.
That's it. Exactly. We are managing energy that desperately wants to escape and burn something down.
Now, just to set the stage for you listening, we are basing this deep dive on a very specific high-level data set today. We are working off the avionics knowledge synthesis and the Session 4 visual curriculum from Project Ampere.
Which is really a gold standard for this kind of technical synthesis.
Yeah, and that is the one and only time we will mention that name, but just know the source material here is dense. It's designed to bridge the gap for professionals. We aren't here to teach you what a switch is.
Right, we assume you already know that.
We're here to move you from just swapping parts to truly understanding the electrical nervous system.
The goal is to move from the what to the why. Any line technician can identify a toggle switch, but do they understand why that specific switch uses silver cadmium oxide contacts?
Or why replacing a switch based just on the voltage ratings stamped on the side might actually cause a fire in the wheel well.
It happens way more often than we'd like to admit. Understanding that difference is really what separates a parts changer from a true avionics expert.
So let's unpack this. Module 1, the physics of switching. I think the average person, maybe even the average pilot, thinks of a switch as a binary device. It's on or it's off. It's just a gate.
That is the functional description, sure. But physically, it is a manager of energy transition. You really have to reframe the switch in your mind.
So what's actually happening when you actuate it?
When you flip the toggle, you are physically tearing apart a path for electrons that are moving at incredible speeds. You are breaking a circuit.
And the electrons do not want to stop.
They absolutely do not want to stop. They carry momentum, primarily in the form of inductance, which we will get to later. But even purely resistive current creates an arc.
Right, because of the air gap.
Yes. When those contacts separate, for a split second, the air between them ionizes. You essentially have a miniature lightning bolt inside that little plastic casing.
So let's look at the hierarchy of actuation that the slides mentioned. We have manual controls, your toggles and push buttons, and we have mechanical ones like microswitches or proximity sensors. But the research highlighted something really specific about the internal architecture.
The material science.
Yeah, specifically silver cadmium oxide.
This is a critical detail that often gets overlooked by technicians. If you were designing a switch from scratch, your instinct might be to use pure silver.
Because silver is the best conductor we have.
Better than copper, better than gold. So in theory, low resistance means less heat, right?
Right, makes perfect sense.
But here is the problem in the real world. Arcing. When that arc forms during the break cycle, the temperature spikes to thousands of degrees. If you have pure silver contacts, that heat melts the surface of the metal slightly.
It creates a tiny molten pool.
Exactly. And then when the switch closes again...
Or even if it opens and just cools down.
Right, specifically if you have a bit of contact bounce, or if the arc is sustained for just a millisecond too long, that molten metal can fuse. When it solidifies a microsecond later, the two contacts are welded together.
So you flip the switch to off, you physically move the lever on the panel.
The lever moves, the internal spring snaps, but the actual contacts are stuck. They're one solid piece of metal now.
So the fuel pump stays on.
The fuel pump stays on or the starter motor stays engaged. You have completely lost control of the system.
That is terrifying. So how does the cadmium oxide actually help mitigate that?
It is an alloy. Silver cadmium oxide. The cadmium oxide particles are dispersed throughout the silver matrix. When that arc hits and the heat spikes, The cadmium oxide essentially decomposes or sublimates slightly.
What does that do to the surface?
It creates a very chaotic surface structure that prevents the silver from forming a solid, coherent bond.
It's kind of like putting sand in the glue.
That is a brilliant way to think of it. It sacrifices a tiny bit of conductivity. I mean, it's slightly more resistive than pure silver, but it gains a massive resistance to contact welding.
It ensures that when you command open, the physics actually allows it to open.
It is the difference between a switch designed for a consumer toaster and a switch designed for a critical flight control surface.
Let's talk about another mechanism for breaking that arc, the double break. The notes highlighted this specifically for momentary switches.
This is all about speed and distance.
Yeah.
Imagine you have a standard single pull switch. You open it and you create one air gap. Let's say it opens to 2 millimeters.
Okay, so the arc has to jump 2 millimeters.
Now, imagine a bridge that lifts from both ends at once. You have a contact bar that moves away from 2 stationary points simultaneously.
So you create 2 separate gaps.
You create 2 2-millimeter gaps instantly. That is 4 millimeters of total air gap achieved in the exact same amount of time.
Yeah.
But more importantly, you divide the voltage stress. If you are breaking a 28-volt circuit, each gap only has to handle 14 volts of potential.
So the arc dies much faster.
Much faster. It creates what we call a thermal shock to the arc. It cools it down and extinguishes it before it can do any real damage to the contact surfaces.
And that's standard in aviation.
It's standard in high-quality aviation switches because it significantly extends the life of the component and reduces the risk of that welding we just talked about.
Now, this leads us directly into the trap you mentioned in the intro, the concept of diverating. For you listening, this feels like the most practical, save your license kind of information in this entire deep dive.
It absolutely is. It is the #1 reason technicians get in trouble with switches. It comes straight from FAA Advisory Circular 43.13-1B.
Walk us through the scenario.
Okay, here's the scenario. You have a circuit that powers a landing light. The light draws 5 amps. You look in the parts bin and you find a switch. The side of the switch says 10 amps, 28 volts DC.
And the logical brain immediately says, well, 10 is bigger than 5. I have a 100% safety margin. I am good to go.
And that logic is completely fatal because that rating on the switch, that 10 amps, is almost always a resistive rating. It assumes a steady, clean flow of current.
But a landing light is not a steady load.
Not at all. It is a lamp load.
So let's break down the physics of the lamp load. Why is a light bulb so violent to a switch?
It comes down to the filament, usually tungsten. When that filament is cold, before you turn it on, it is a very, very good conductor. Its resistance is incredibly low. It's almost a dead short.
Okay, applying Ohm's law here. The voltage is fixed at 28 volts. If the resistance is near 0,
current goes to the moon. For the first few milliseconds, typically 10 to 50 milliseconds, that 5-amp light bulb isn't drawing 5 amps. It is drawing inrush current.
How high does that go?
That inrush can be 15 to 20 times the operating current.
Wait, so 15 times 5. We are talking 75 amps.
75, maybe even 80 amps. Slamming through that tiny switch the exact instant the contacts touch.
And I just installed a 10-amp switch.
Exactly. You just hit a 10-amp component with an 80-amp hammer. The contacts will pit, they will erode, or like we discussed earlier, they will spot weld shut.
So the switch fails, the light stays on, or worse, the switch overheats and literally melts the panel.
So what is the fix? What does the FAA tell us to do?
You have to derate.
You have to derate. For a lamp load, the derating factor is typically around 5.0 to 8.0. You do not size the switch for the 5 amps it uses while it's just sitting there running.
You size it for the violent moment of startup.
You size it for the inrush. You need a switch capable of handling that initial spike without degrading the contacts.
So for a 5-amp lamp, I might actually need a switch rated for 40 or 50 amps.
Roughly, yes.
Yeah.
Or you verify that the switch manufacturer has already accounted for lamp loads and given it a specific lamp rating, but you never, ever trust the nominal resistive rating on the casing without knowing the load physics.
And it isn't just lamps, right? Inductive loads are the other beast entirely.
Inductive loads, your solenoids, relays, motors, they're the exact opposite problem. Lamps hurt you when you turn them on. Inductive loads hurt you when you turn them off.
This is the magnetic field collapsing.
Yes. An inductor stores energy in a magnetic field. When you open the switch, you cut the power. The magnetic field has nothing holding it up, so it collapses.
And physics dictates a reaction.
Lenz's law, specifically. It says that the collapsing field will induce a current to oppose the change. It essentially tries to force the electricity to keep flowing across the physical gap you just opened in the switch.
It forces an arc.
A massive, sustained arc. We call it the inductive kick. It violently burns the contacts as they separate. So for inductive loads, you also have to deperate significantly, usually by a factor of 2 to 4, just to handle that abuse on the brake cycle.
It really changes how you look at a switch panel. It is not just a row of plastic levers anymore. It's a row of complex energy management decisions.
Every single switch is meticulously matched to its load, or at least it absolutely should be if the technician understands the design.
Before we leave switches completely, let's talk about the niche types mentioned in the Ampere slides, specifically the locking lever toggle, the pull to unlock.
A classic design. You have
Yeah.
definitely seen these. The lever is locked in a physical detent. You have to grab the top of the lever, pull it out against a spring before you can move it up or down.
It's very tactile, very satisfying to use. But why is that extra mechanical step there?
It is all about cognitive friction. We use these for critical systems. Fuel shutoff valves, fire extinguishers, generator disconnects.
Things you don't want to bump with your knee.
Exactly. In a cockpit, things happen fast. Severe turbulence is shaking your hand. You might drop a clipboard. You absolutely do not want a stray bump to shut down an engine in flight.
So it forces a deliberate, conscious action.
It forces your brain to engage with your hand. The mechanical motion is complex enough that it cannot happen by accident. It acts as a physical, are you sure, tie log box.
I love that analogy. And on the completely other end of the spectrum, we have the microswitch, the precision logic device.
The snap-acting switch. If you look at an aviation schematic, the symbol for this is often a little circle with a dot in the middle. That dot means snap action.
Why does the snap matter so much?
Imagine you are using a switch to detect if the heavy landing gear is fully down and locked. The gear mechanism moves relatively slowly. If you used a standard switch, as the gear pressed against it, the internal contacts would close very slowly.
So you'd get a period of time where the contact is sort of mushy.
Exactly. Maybe it connects, maybe it doesn't. Maybe vibration causes it to bounce. Maybe it just sits there in arcs.
You definitely do not want mushy data on your landing gear status.
You need absolute certainty. A microswitch has an internal spring mechanism, usually an over-center beryllium copper spring that builds up mechanical tension.
So the plunger moves, but the contacts don't.
The plunger moves, it builds tension, builds tension, builds tension, and then snap. It violently changes state in milliseconds, regardless of how slow the external plunger is moving.
It completely eliminates the transition state.
Exactly. It digitizes the analog world. It gives the flight computer a flawlessly clean 0 or 1.
This is a perfect bridge to Module 2, electromechanical logic. Because now we are moving away from the manual switches in the pilot's hand to the heavy lifting, the action at a distance concept.
This is really the great leap in modern aviation design. If you look at a DC-3 or a World War II bomber, the cockpit was filled with heavy copper cable.
Because the power went right to the switch.
Right. If you wanted to turn on the landing light, the massive cable came straight from the battery, all the way into the cockpit to the switch, and all the way back out to the wing.
That is a staggering amount of heavy copper.
It's heavy, which kills payload, and it's incredibly dangerous. You are bringing high amperage lines right behind the instrument panel. If that chafes and shorts out, you have a massive electrical fire right in the pilot's face.
So the modern philosophy, really the Boeing 747 era and beyond, is remote operation.
Correct. The cockpit switch becomes merely a signaling device. It carries maybe half an amp on tiny lightweight wires. It talks to a relay or a contactor located way back in the E&E bay, the electronics and engineering bay.
And that relay is what actually connects the heavy power to the load.
Exactly. It isolates the pilot from the raw power.
So let's distinguish between the two main players here, solenoids and relays. I feel like these terms get used interchangeably all the time, but they are fundamentally different beasts.
They are cousins, but they have very different jobs. A solenoid is a physical worker. It does linear mechanical work.
Like a starter solenoid engaging an engine.
Exactly. A starter solenoid has a heavy iron plunger inside it.
Duh.
When you energize the coil, it creates a magnetic field that physically shoves that heavy plunger forward.
And that movement engages the actual starter gear with the engine flywheel.
Right. It moves mass. It performs mechanical labor.
So solenoid equals mechanical movement.
Ideally, yes. Whereas a relay is strictly a logic device. It has a very lightweight armature, usually just a little hinged plate. When the electromagnet pulls it, it doesn't move a heavy gear, it just closes a set of electrical contacts.
It's essentially a remote-controlled switch.
Precisely.
Now, the physics of that pull, the actual snap of the relay, is governed by Ampere's law. And the deep dive notes pointed out something fascinating about the air gap.
This is the key to understanding why aircraft relays sound the way they do. The force of the electromagnet is determined by the current and the number of turns in the copper coil, divided by the distance, the air gap squared.
Squared. So the force is exponential as it closes.
Highly exponential. When the relay is fully open, the gap is wide.
Mm.
The magnetic pull is at its weakest, just barely enough to start pulling the armature against the spring.
But as soon as it starts moving...
As the armature moves closer, the physical gap shrinks.
Right.
As the gap shrinks, the magnetic force skyrockets exponentially.
Plus it constantly accelerates.
It literally slams shut. That distinct hard click you hear isn't just for show, it is physics. We desperately want that high-speed closure to minimize contact bounce and ensure a solid connection.
Because if it closed slowly, the contacts would flutter and burn under the load.
Exactly.
But there is a very dark side to all this concentrated magnetic energy. We touched on it briefly with switches, but let's go deeper. Back EMF, the ghost in the machine.
This is the invisible killer of avionics. When you have a relay coil energized, you have a very stable magnetic field. That field represents stored kinetic energy. It was like a stretched rubber band.
And when you turn the switch off and kill the power...
You cut the source current. The magnetic field suddenly has nothing to sustain it, so it collapses inward. And it collapses essentially at the speed of light.
And as those magnetic lines of flux crash inward...
They violently slice through the copper turns of the relay coil itself.
And we know from basic physics that a moving magnetic field induces a voltage in a conductor.
Correct. But because the field is collapsing, the voltage is reversed. It flows backwards against the original current. And because the collapse is so incredibly fast, the induced voltage spike is massive.
Give me a sense of scale here.
You might use just 28 volts to turn the relay on, but when you turn it off, that coil can spit back a transient spike of negative 500, 800, maybe even 1,000 volts.
A 1,000-volt spike on a delicate 28-volt digital system. That sounds catastrophic.
If that spike gets out onto the common electrical bus, it searches for the weakest link. Usually that is a sensitive transistor in a flight control computer or a GPS unit or a comm radio.
And it just punches right through the silicon.
It completely punches through the microscopic PN junctions. The component is fried instantly, permanently dead.
And from a pilot's perspective, you wouldn't even know why. You just turned off a landing light and suddenly your primary GPS goes dark.
Exactly. It's a nightmare to troubleshoot. So we have to cage the beast at the source. We use suppression.
Flyback diodes.
That is the most common and robust method. We install a tiny semiconductor diode across the coil terminals of the relay, but in reverse bias.
Walk me through exactly how that works.
So under normal operation, the diode is facing backward to the 28 volts. It blocks the current. It sits there and does absolutely nothing.
It's invisible to the system.
But when you open the switch and that back EMF spike happens, that massive reverse voltage, the diode sees it in the forward direction and instantly opens the gate.
So it creates a localized short circuit?
It creates a closed loop right at the coil. The energy circulates harmlessly through the diode and the coil, round and round, dissipating its thermal heat over a few milliseconds until it completely dies out.
It literally heats the spike.
It eats the spike so the rest of the plane doesn't have to. If you look at any high-quality aviation relay, you will often see that suppression diode built right into the internal casing. It is the silent bodyguard for the entire avionics suite.
Speaking of high-quality relays, let's talk about environmental hardening. The notes mention the Leach KM series relays, which are rated for 200 Gs of shock. 200 Gs.
It sounds totally excessive, doesn't it? I mean, a human pilot passes out at 9 Gs. The airframe itself might literally snap in half at 15 Gs. Why on earth do we need a 200 G relay?
That is exactly what I'm asking.
It is not about sustained G-force like in a tight turn. It is about severe mechanical shock and vibration. Think about where these relays actually live.
In the engine nacelle.
They might be mounted directly on a firewall, mere inches away from a massive jet engine vibrating at tens of thousands of RPM. Or think about a hard, violent carrier landing for a Navy F-18. The immediate impact is a massive, sharp shock wave traveling through the airframe.
And a normal industrial relay would fail under that.
A standard industrial relay uses a very simple linear spring to hold the contacts open. If you hit it with a sharp shock wave, the physical inertia of the heavy armature might momentarily overcome that spring.
The contact bounces closed for a split second.
Exactly.
So the cabin lights flicker.
Or the autopilot abruptly disengages. Or the engine fire bottle fires into the cowling. We absolutely cannot have uncommanded activations due to vibration.
So how do you harden it against that?
Aviation relays are heavily mass balanced. The internal armature is meticulously designed so that its center of gravity is exactly at the mechanical pivot point.
Oh, so linear shock doesn't apply any rotational torque.
Exactly. You can hit it with a hammer, and the armature will not rotate. It physically requires a dedicated asymmetrical magnetic pull from the coil to make it move.
That is brilliant engineering. It makes it completely immune to the kinetic environment.
And then there's the atmospheric sealing, hermetic seals, glass-to-metal fusion around every single terminal.
Because an airplane breathes.
It constantly breathes. It goes from sea level pressure up to 40,000 feet where the air is incredibly thin and freezing, and then back down into a hot, humid jungle runway.
If the relay wasn't perfectly sealed, it would just suck in all that moisture.
It would breathe in humid, wet air on every single descent. That moisture would immediately condense inside the casing. You would get severe contact fouling, corrosion, ice formation, and eventually catastrophic failure.
So they seal them tight and fill them with an inert gas.
We seal them and typically backfill them with bone-dry nitrogen. It locks out the environment permanently.
All right, moving on to Module 3, the science of protection. We have talked extensively about controlling the power. Now let's talk about saving the system when things inevitably go wrong.
The guardians of the bus. Circuit breakers and fuses.
There is a golden rule here that I think surprises a lot of people who are outside the aerospace industry. The circuit breaker does not exist to protect the device.
Say that again for everyone listening. It is the single most misunderstood concept in electronics.
The circuit breaker exists solely to protect the wire.
Correct. The EDO-UIS, the electrical wiring interconnection system. If your landing light shorts out internally, it is already broken.
Yeah.
The breaker cannot magically save the light bulb.
The breaker's only job is to stop the wire that feeds that light bulb from turning into a glowing heating element.
Because if the wire gets red hot inside the airframe,
it melts its Teflon insulation.
It melts the insulation. It burns into the critical wire bundle next to it. It ignites the hydraulic fluid dripping nearby. It literally brings down the plane. The breaker is there to cut the power long before the wire reaches its smoke-generating temperature.
Let's look at the actual mechanism of protection. First, fuses. They seem so archaic. Why do we still even talk about them in modern aviation?
Because they are flawlessly simple, inherently reliable, and significantly lighter than mechanical breakers. But the physics of the slow-blow fuse is really worth unpacking.
Slow blow almost sounds like a manufacturing defect.
It sounds like it's just lazy, but it is actually a highly engineered concept called thermal inertia. Remember the electric motor we talked about?
Yeah.
The one with the massive inrush current.
The 75 amp starting spike on a 5 amp system.
Right. If you put a standard fast-acting fuse on that motor circuit, it would blow every single time you tried to start it. It would see 75 amps and instantly say, too much pop.
So you would literally never get the motor running.
You'd be grounded. A slow-blow fuse is specifically designed with a heavy thermal mass. It sees that 75 amp spike, and it essentially says, whoa, that is way over the limit, but I am going to wait.
It absorbs the heat.
It absorbs the thermal energy for maybe 500 milliseconds. If the current drops back down to the normal 5 amps, it cools off and we are good. But if it stays at 75 amps, then the element finally melts and clears the fault.
It filters out the normal startup noise.
It intelligently distinguishes between a harmless transient surge and a dangerous permanent fault. That is measured by the I²T rating, the current squared multiplied by time.
Now, what about standard circuit breakers? The bimetallic strip. This is the absolute standard you see on the cockpit panels.
It is essentially a mechanical thermostat that kills the power. Inside the breaker, you have two dissimilar strips of metal, molecularly bonded together, usually something like brass and Invar.
And they react differently to heat.
Dramatically differently. Brass expands quite a bit when it gets hot. Invar, which is a specialized nickel-iron alloy, hardly expands at all.
So when the overload current flows through them, resistive heating causes them to get hot.
And because one side desperately wants to grow longer and the other side refuses to stretch, the entire strip is forced to physically curl. It bends.
And if the current is too high for too long,
it bends far enough to actuate a delicate internal sear. Snap. The latch releases, the contacts fly open, and the white button pops out on the panel.
But because the entire mechanism relies heavily on ambient heat to work, the temperature of the cockpit matters, right?
It is a massive variable. If you are parked on the ramp in Phoenix, Arizona in July, and the flight deck is 140 degrees, those breakers are already incredibly hot before you even turn anything on.
They are pre-biased towards tripping.
They will absolutely trip at a much lower current threshold than they would if you were flying over Alaska in the winter. Manufacturers have to provide very specific derating curves for ambient temperature to account for this physical reality.
Now, I really want to talk about a specific FAA regulation that I found totally fascinating in the source material. 14 CFR Part 25.1357, the trip-free requirement.
This is a regulation entirely born from human psychology and pilot panic.
Set the scene for us.
Imagine a pilot in a highly critical emergency situation. Say there is smoke in the cockpit. Primary systems are failing. The stress is unimaginable. Suddenly, a circuit breaker for a vital comm radio pops out.
The pilot instinctually pushes it right back in.
It pops out again. The pilot is desperate to talk to air traffic control. They push it in and literally hold their thumb on it. They think, I am going to physically force this circuit to work.
I am the captain, and I command this radio to function.
And the trip-free regulation essentially says, I am sorry, Captain, but I can't let you do that.
It completely overrides the human operator.
The internal mechanical latch is explicitly designed so that the electrical contacts release independently of the external push button. Even if you tape that button down, even if you hold it in with vice grips, if that bimetallic strip bends from an overload, the circuit opens internally anyway.
You physically cannot force a faulted circuit closed.
You cannot override the laws of thermodynamics. This brilliantly prevents the terrified pilot from inadvertently holding a dead short circuit closed and turning the aircraft wiring into a catastrophic fire starter. It saves the human from their own desperate instincts.
That is just profound engineering. And finally, in this protection module, selective coordination, the Christmas tree effect.
Coordination is all about hierarchy and isolation. Imagine a main power bus that feeds 10 different non-critical subsystems, a coffee maker, reading lights, foot warmers. That entire main bus is protected by a large 50-amp breaker.
But each individual item has its own smaller breaker, too.
Right. The coffee maker has a 5-amp breaker. The lights have 1-amp breakers.
So if the heating element in the coffee maker severely shorts out to the chassis,
you desperately want that specific 5-amp coffee maker breaker to pop immediately.
Yeah.
You do not want the main 50-amp bus breaker to pop.
Because if the main one pops, you lose the reading lights, the foot warmers, everything on that bus.
You unnecessarily lose the entire power distribution node.
So the little downstream breaker has to be fundamentally faster than the big upstream breaker.
Always. The protective device physically closest to the electrical fault must be the absolute fastest to clear the fault. If your main breaker reacts faster than your downstream breakers, you have a poorly designed, uncoordinated system.
You'll have nuisance trips everywhere.
You will take down perfectly healthy aircraft systems along with a single bad one, which is unacceptable in flight.
Let's transition to Module 4, the hostile environment. We talked about heat and vibration, but altitude is really the weird one. Paschen's law.
Paschen's law describes the exact breakdown voltage required to start an electrical arc in a specific gas, like air, based on the ambient pressure and the physical distance between the contacts.
I think most people intuitively assume a vacuum is a perfect insulator. So going to high altitude means better insulation, right?
And that is the common intuition, but it is dead wrong. As you go higher in altitude, the atmospheric air density drops. The actual air molecules get physically further apart.
Which increases the mean free path of an electron.
Exactly. When a stray electron is accelerated by the voltage potential between two switch contacts, it can travel much further through the thin air before it finally collides with a gas molecule.
So it builds up speed.
It builds up tremendous kinetic energy. When it finally does smash into a molecule, it hits it incredibly hard. Hard enough to violently knock other electrons loose from their orbits.
It creates a chain reaction. An avalanche.
Massive ionization.
So the electrical arc forms much easier in thin air than at sea level.
Up to a specific point, yes. There is a sweet spot called the Paschen minimum, a true danger zone. For typical unpressurized aircraft voltages, this danger zone sits right around 60,000 to 70,000 feet.
Which is standard cruising altitude for high-end business jets and military aircraft.
Exactly. At that specific altitude, the air is electrically very weak. A switch that opens cleanly at sea level might act exactly like an engine spark plug at 60,000 feet. The arc strikes across the gap, and it absolutely refuses to extinguish.
It just sits there and burns up the switch.
It burns until the metal vaporizes.
So how do we engineer around that? We obviously can't change the atmosphere outside the plane.
We change the local atmosphere inside the component. We use hermetically sealed relays filled with highly pressurized nitrogen, We essentially keep the dense sea-level atmosphere trapped inside a little box.
Or we use special arc-quenching gases.
Like sulfur hexafluoride, SO6, which is a very heavy, dense gas that aggressively suppresses arcsing. Or if we must use unsealed components, we simply design the internal mechanisms with massive physical air gaps, much wider than you would ever need on the ground, to physically stretch the arc until it breaks.
Next environmental threat, and this one is crazy. Tin whiskers. This sounds like something out of a fantasy novel, but the research specifically references IPCTR 446.
It is the absolute scourge of modern aerospace electronics.
Mhm.
And the tragic part is, it is essentially a self-inflicted wound caused by very good environmental intentions.
Explain that history to us.
Historically, pure tin is used to plate the metal terminals and contacts of electronic components to prevent corrosion and make soldering easier. Pure tin has a very specific crystalline lattice structure. When it is plated heavily onto a copper substrate, immense internal mechanical stresses build up inside the tin lattice.
It's under pressure.
Over time, and this can be months, years, or even decades, the pure tin attempts to relieve this internal stress by physically pushing out long microscopic filaments of metal.
These are the whiskers.
Yes,
It's kind of like squeezing a tube of toothpaste from the bottom.
exactly like that, but on an atomic scale. These whiskers are pure, highly conductive tin, and they can slowly grow up to 10 millimeters long.
Now, in the 1950s or 60s, a 10-millimeter whisker really didn't matter. The components were huge and spaced far apart.
Right, vacuum tubes and large relays. But today, on a densely packed surface mount microchip, the tiny pins are literally 0.5 millimeters apart. A 10-millimeter conductive whisker is like throwing a massive steel bridge across the Grand Canyon.
It perfectly shorts the microscopic pins together.
It creates a dead short, and the system instantly fails. Multi-million-dollar satellites have been completely lost to this. Medical pacemakers have been urgently recalled.
And here's the good intentions part you mentioned earlier. The absolute best way to stop these pure tin whiskers from growing is to heavily alloy the tin with lead.
Exactly. Lead, PB.
But lead is highly toxic. The global RoHS directive essentially banned it everywhere.
Exactly. The massive consumer electronics world, your smartphones and laptops, were completely lead-free to be environmentally green. But injecting lead into the tin disrupts that pure crystal structure and completely eliminates the internal stress. It completely prevents the whiskers from ever forming.
So the aviation and aerospace industries had to say, hold on a minute, we cannot have airliners falling out of the sky a decade from now because of invisible microscopic whiskers.
So there is a massive regulatory conflict. Aviation explicitly requires leaded solder and leaded component finishes, usually a minimum of 3% lead.
But the global electronics supply chain is dominated by consumer tech that demands lead-free parts.
Which creates a terrifying risk of COS, commercial off-the-shelf parts, silently sneaking into the aerospace supply chain. If an aviation technician blindly buys a generic logic chip or a relay from a standard electronics distributor, it will almost certainly be lead-free.
It might work perfectly today, but it might fatally grow whiskers in 5 years while cruising over the ocean.
That is the hidden, creeping danger. We have to meticulously audit the metallurgical pedigree of every single component.
Incredible. Finally, in this module, let's look at radiation hardening.
Cosmic rays. Highly energetic subatomic particles from deep space and solar flares. The thick atmosphere mostly protects us down here on the ground, but at 40,000 feet, the aircraft is taking a lot of microscopic hits.
And these high-energy particles can actually physically alter a computer's memory.
They cause single-event upsets. A microscopic particle blasts through a silicon memory cell, deposits an electrical charge, and a binary 0 instantly becomes a 1.
The flight computer suddenly gets deeply confused.
Or worse, you get a latch-up, where the particle's kinetic energy causes a microscopic transistor to get permanently stuck open, creating a localized short circuit that rapidly burns out the entire silicon chip.
So to fix this, do we need incredibly advanced, highly shielded, futuristic microchips?
Paradoxically, no. The smaller and more advanced the chip features get, like modern 7-nanometer architecture, the easier they are to utterly destroy. A single cosmic particle is physically huge compared to a 7-nanometer transistor.
It wipes it out, so older is actually better here.
Bigger is physically better. Old school, bulky, bipolar transistors, and yes, even heavy electromechanical relays are inherently rad-hard by their very nature.
They are essentially too big and too dumb to be bothered by a tiny cosmic ray.
Exactly. It doesn't deposit enough energy to flip a large mechanical state. That is exactly why you still see robust, 1980s era processing tech in critical flight control computers. It is not because aerospace engineers are cheap or lazy. It is purely because that old architecture actually survives the high-altitude radiation environment.
Moving into Module 5, Troubleshooting Logic and Systems Integration. This is where we bring all this deep physics back to the technician working on the flight line.
The line detectives.
Schematic intelligence. You talked earlier about looking for the dot on the microswitch symbol. Let's talk about the logic of rotary switches and the break-before-make concept.
This is absolutely crucial for safe power source selection. Imagine a physical rotary dial on the overhead panel. Position 1 is engine generator A. Position 2 is engine generator B. You're manually switching the aircraft bus between them.
As you turn the knob with your hand, the internal metal wiper physically moves across the contacts.
Now, if that metal wiper touches contact 2 before it fully leaves contact 1, what physically happens?
You have just accidentally bridged generator A directly to generator B.
You have paralleled two massive, completely unsynchronized, alternating current power sources. They will instantly fight each other. Terrifyingly huge currents will flow between them.
You might literally shear the mechanical drive shaft of the generator right off the engine.
You will cause catastrophic mechanical damage.
So the switch mechanism must mechanically disconnect fully from the old source before ever touching the new source.
That is the definition of break before make. And on a proper wiring schematic, you can actually see this visual logic. The drawn gap between the contact plants will be physically wider than the drawn width of the moving wiper.
So a really sharp technician looks at that abstract drawing and instantly verifies, okay, this architecture guarantees a safe, isolated transition.
It's about reading the physics in the ink.
Let's talk about the automated logic of the split bus architecture. We see this heavily on aircraft like the Boeing 737 or the Airbus A320.
The overarching philosophy is total redundancy. You have a left main bus and a right main bus. Normally, they are completely electrically separate. The left engine generator feeds the left side. The right engine generator feeds the right side.
But obviously, if you lose an engine in flight,
the heavy bus tiebreaker instantly closes to connect the two sides together. But the complex part is the priority logic. The system is hard-coded to constantly prioritize specific power sources.
The slide deck specifically mentioned a Boeing rule. Last source takes priority.
In many Boeing automated systems, yes. Imagine you are sitting at the gate running off the tail APU, the auxiliary power unit. Then the ground crew plugs in the heavy ground power cable.
When you reach up and flip that ground power switch on the panel,
the automated bus logic says, a new power source has been manually commanded. I have checked it. The voltage and frequency are good. I will blindly accept it.
And it does the switching automatically.
It forcefully opens the APU contactor and instantly closes the ground power contactor.
It prevents the human from accidentally crashing the two sources together.
It acts as a high-speed, automated traffic cop. It ensures seamless power transfer entirely without relying on human perfection.
And finally, we have to talk about diagnostics. We need to cover the smoke test and the infamous voltage drop test.
The smoke test is obviously a dark, tongue-in-cheek name for verifying your wire sizing against your protection. If a circuit breaker keeps repeatedly popping on the line, the incredibly lazy, dangerous fix is to just shove in a bigger breaker.
Oh, the 5 amp keeps popping. Just put in a 10 amp and ship the plane.
And we just spent half an hour discussing exactly why that is lethal.
Because of the wire's thermal limit.
Because of the wire. If the physical wire is 22 gauge, it is thermodynamically rated to carry maybe 5 to 7 amps safely. If you artificially slap a 10 amp breaker on it and a hard short occurs, that thin wire will literally glow red hot and catch fire long before the oversized breaker ever trips.
You have fundamentally made the aircraft wire the new fuse.
And aviation wire makes a terrible fuse because it sets the entire airframe on fire. Always check AC 43.13, table 11 to 9. You meticulously match the breaker rating to the physical wire gauge, not to whatever the load demands.
And lastly, voltage drop testing. Why do you so passionately hate the beep mode on digital multimeters?
I really don't hate the tool itself, but I deeply hate how it is lazily misused by technicians. Continuity testing, the beep, only tells you if the circuit resistance is less than an arbitrary number, say 50 ohms.
So it confidently beeps if there is any physical connection at all.
But is it a robust current-carrying connection? A single microscopic strand of frayed copper wire left intact on a massive power cable will make the meter beep happily.
A heavily corroded switch contact full of carbon will make it beep.
Exactly. But try to actually push 20 amps of working current through that single frayed strand.
It will instantly fail or burn up.
It will create massive localized resistance. High resistance fundamentally causes a severe voltage drop. So your expensive pump motor only receives 18 volts instead of the required 28. It runs dangerously slow or it overheats.
So how do you reliably find that invisible resistance?
The only guaranteed way to find it is dynamic voltage drop testing. You must measure the voltage physically across the switch while the circuit is heavily loaded and active.
You measure directly across the switch terminals.
Yes, put 1 meter probe on the input terminal and the other probe directly on the output terminal of the closed switch. If the internal contacts are perfect, the voltage difference between those 2 points should be exactly 0.
But if you see a difference?
If you see 0.5 volts or a full volt dropping across that switch, that tells you the switch itself is eating that electrical energy and turning it into heat. It is failing internally. Replace it immediately.
That is the absolute golden rule of advanced electrical troubleshooting.
Never blindly trust the continuity beep. Only trust the dynamic voltage drop under load.
We have covered a truly massive amount of ground today. From the sublimation physics of cadmium oxide to the ionization of thin air at 60,000 feet.
It is an incredibly complex, unforgiving ecosystem.
If you had to distill the entire mission of this deep dive, the singular takeaway for the professional listening, what is it?
It absolutely all comes back to this signature in the logbook. When you, as a line technician or a systems engineer, sign that maintenance release or approve that engineering drawing, you aren't just verifying a part number against an IPC.
You are certifying the underlying physics.
You are stating on the legal record, I have personally verified that the thermal, magnetic, and environmental properties of this specific component are fully capable of containing the violent energy of this aircraft under all flight regimes.
You are the ultimate guardian of the nervous system.
That is the fundamental job description.
And just briefly, looking forward to the future, the Ampere notes mention SSPCs at the very end.
Solid-state power controllers. We are aggressively moving away from clicking mechanical relays and heavy biotalic breakers toward completely silent, silicon-based electronic switches.
Because they are smarter, right?
They are incredibly programmable, they are fast, they can actively report their own thermal health, and exact current draw directly to the flight computer.
But there is always a catch.
The massive catch is they are incredibly delicate. They are hypersensitive to ESD, electrostatic discharge. A technician simply walking across a synthetic carpet without wearing a proper grounding strap can instantly destroy a $10,000 SSPC just by brushing against the connector pins.
So the physics of protection completely shifts from heavy mechanical hardening to extreme static hygiene.
The physical tools change entirely, but the deep need for theoretical understanding remains exactly the same.
Listeners, here is your final challenge for the week. Next time you pull out a complex wiring schematic, don't just blindly trace the solid lines from point A to point B. Actually look closely at the component symbols.
Look at the dots, the dash mechanical links, the visual air gaps.
Ask yourself, what is the violent physical behavior deeply hidden in this static ink? Try to mentally visualize the bimetallic strip curling under extreme heat. Visualize the invisible magnetic flux violently collapsing when the switch opens.
That is exactly where the true aha moments live for a master technician.
Thanks for diving deep with us today. Fly safe out there.
And always keep the smoke on the inside of the wire.